Hi, I'm James. Today I'll be talking about the network-based rating system and its resistance to bribery. So in this paper, we are introduced to two types of rating systems. The first one is called the objective rating or the all rating, where individual evaluations are aggregated and then is seen as a single figure, which can then possibly influence a potential customer. Also, there's the personalized rating or the peer rating, which is the case where the customer only receives the evaluation given by a set of trusted peers, such as the customer's friends or family, and only this set of information influences the decision of the customer. So the main research goals in this paper was to analyze the effect of bribing in both all rating and peer rating under various constraints and show possible conditions where the system is bribery proof. So we'll go over a few definitions commonly used in this paper. So we have the framework where there's an object R called the restaurant, and this is evaluated by a finite non-empty set of individuals called C, which is the customers. And these customers are connected by an undirected graph of E, and we denote the neighborhood of customers as NC. And these customers submit an evaluation drawn from values of the interval 0 to 1, or they express no opinion as the star sign as shown in the slide. And this evaluation can be seen as a function that maps the customer to a value they evaluated to. And we define V as the subset of customers that expresses an evaluation over the restaurant. So the set of customers who voted. So under these definitions, we can express all rating as a following equation, where it is the average of all evaluations given by the customers. And if we assume that the utility that a restaurant gets is proportional to its rating, we can say that the utility is equal to the all rating multiplied by the number of customers. Now let's define strategy as a function sigma, such that we are giving a additional value to the original evaluation the customer had, and we impose that the additional values the customer adds, when we round it all up for all customers, this sum cannot go over the initial utility that the restaurant had. So we now show evaluation after execution of the strategy as the either 1, which is the maximum value that a customer can assign to a restaurant, or the sum of the original evaluation and the bribed amount. Now, when the customer originally expressed no opinion, the bribed amount will add directly on top of it, and if the bribed amount is 0 and the customer didn't express any evaluations, that will remain the same. So the resulting utility for the restaurant after the bribing will be shown as in the equation, which is the evaluation obtained after the bribing minus the amount of money spent. Now for peer rating, we can adapt the previous definitions as follows. So peer rating, which is average of all evaluations of neighbors of a given customer, it can be shown as in the first equation, and the utility as seen by the second equation, is the sum of all P rating for every customers. And by adapting what we had for the O rating, the utility after bribing can be seen as follows in the third equation. So now let's take the first case of O rating where everybody voted, hence V is equal to C. Now if we say that two strategies are disjoint, if the set of people bribed by each strategy is completely different, then it follows that the revenue of combining such strategies will be equal to that of the sum of revenues of each individual strategies combined. Then we can also show revenue as a difference between the utility after bribing and the original utility. And by rearranging the equation as shown on the slides, we can see that this value is always less than or equal to 0, meaning no matter what bribing strategy it is, bribing one person is never profitable. Then we can go on to say that any bribing strategy can be decomposed into any n pairwise disjoint strategies, meaning we can apply the first and the second lemma to say that no strategy can be profitable when everybody votes in O rating. So let's go on to the second case where there's non-voters in O rating system. So in the given example, we can show that there are 3 customers where A and B evaluates as 0.5 originally, while C has no opinion. Now the original utility in this case will be 1.5. If we let strategy 1 be bribing A 0.5 and then strategy 2 to be bribing C 0.5, then we can see that the resulting utility for strategy 1 is 1.75, while for strategy 2 it's 1. But then combining these two strategies together results in a utility of 1, which means that the lemma 1 from the all vote case does not hold anymore. And it also shows that in case of strategy 1, the O rating is not bribery proof for this case. So let's try to find a dominating strategy. We say that C bar is a customer that hasn't voted, and C bar greedy restriction of a strategy sigma involves eliminating the customer who hasn't voted from the set of voters, and then the greedy restriction doesn't spend any further resources on this customer, but rather redistributes what would have gone to this customer among the remaining voters. Then we can go on to show that this imposing greedy restriction is always better than not imposing it by this equation, where the difference between the utility of imposing the greedy restriction and not the original one is always going to be larger than 0. So from this we can say that a strategy is weakly dominant for O rating if and only if it is a greedy strategy, because the O greedy strategy has equivalent payoff, and bribing non-voters are always dominated by bribing voters, and then this follows to that it is always profitable to bribe as much as possible. And non-greedy strategy will bribe either a non-voter or it will not always bribe as much as possible. So it is not always weakly dominant. So now let's go into the P rating. We introduce a new concept called the influence weight of a customer, which is how much of a weight their rating has compared to the neighbors. And now, using this influence weight, we can show the original equation from the previous slide as given in the lemma 6. Now let's take a case of P rating where everybody votes. Then we can express revenue as given in the proposition 8 by rearranging the equation after expressing it as a difference between the original utility and the bribed utility. In a case given in this slide, we let a network structure be a 4-arm stars where A in the center is connected to 4 other customers. Now, if we assume that everybody has evaluated the restaurant 0.5 originally, and we have weighting of 2.2 for A and 0.7 for everybody else, when we consider 2 strategies of either bribing A with 0.5 or bribing anyone else with the same amount, we can see that the revenue of bribing A is 0.6 while bribing B, which is the non-centric customer, is minus 0.15, showing that bribing a customer with weighting less than 1 is actually resulting in a negative revenue. So we can have this strategy where we order each customer according to their influence weight, and starting from the customer with the highest influence weight, we bribe them until we run out of the budget. And we can see from the previous proposition of definition of the revenue that this strategy is weakly dominant, meaning that this system is not bribery proof. Now in the case where everybody votes but the network structure is unknown, we can express the expected revenue as given in equation 5, and by rearranging the equation we can see that the expected revenue is 0 in all cases, meaning that when the network structure is unknown, the expected revenue is 0. So in this case we are bribery proof. So now let's take a case for P rating where we have known voters, where we have 4 individuals B, C, D, E connected to a known voter A in the middle. Now if we say that they originally evaluated the restaurant as 0.2, then we have the P rating or utility of 1. And now if we have a strategy where we bribe A, which is the customer in the center, and only A, then the resulting utility is 1.76, which is higher than the original utility, showing that it is profitable to bribe. And it is possible to show that any other strategies are dominated by this strategy. And when we have a known network such as this with known voters, then similar to that of when everybody voted, we can express the revenue as follows, and this will always evaluate to be positive if we bribe people who have rating higher than 1. Lastly, when we have known voters in an unknown network structure, we can then evaluate the case with 3 customers for every permutation possible that revenue can be positive in certain cases, showing that P rating is not bribery proof even in presence of known voters and the network is unknown. So in conclusion, both P rating and O rating are not bribery proof in general, while they do have certain conditions that are, but the impact of bribing on 2 systems is quite different, because in O rating you only require 1 person to be bribed, which will affect every other individuals, while for P rating there could be cases where there are very large proportions of known voters or participants with really few connections.